In 2010, 3 researchers at Boulder watched a ceramic that normally takes hours at 1450 degrees turn solid in under 5 seconds at 850. One voltage, one small disk, a current trace that nearly tripped the supply. By the time anyone could blink, the puck had shrunk, the trace had plateaued, and the timer had stopped. The result was so impossible that for a year, other labs assumed the experiment was wrong. How can a small voltage replace a 1600-degree furnace? And 15 years later, why do the people who study this for a living still argue about what is happening inside the sample? Start with powder, gray, dry, dusty, the kind of stuff you would pour out of a bag. It is the raw material of every ceramic object in your house. Press it into a disc. You get what ceramicists call a green body, fragile, porous, about 60% of full density. You could crumble it between your fingers. So you put it in a furnace, a very large furnace. And you wait. Inside, at 1400 degrees Celsius, something slow and remarkable is happening. The grains are not melting. Ceramics with strong covalent bonds barely melt at all. Atoms creep, one at a time, across the boundaries between grains. They fill the pores, they fuse the necks. After several hours, the green body has shrunk by about 20%, and reached 99% of theoretical density. That is sintering. Powder made into pottery, by diffusion, below the melting point. It is how the white insulator inside a spark plug is made. How dental crowns are made. How ceramic brake discs are made. The white substrate under nearly every microchip in the room you are sitting in, sintered. It is, depending on who you ask, the second or third most energy-intensive step in industrial ceramics. A modern sintering furnace can draw the power of a small town for an afternoon. And it runs hot, 1400 Celsius for zirconia, 1600 for alumina, 1700 for the hard stuff. For hours, sometimes a full day. And it is not just the energy. The slow heating gives grains time to grow. Big grains mean weaker parts. Microstructure control is half of material science, and conventional sintering hands a lot of it to thermodynamics. Why so hot? Why so slow? Because the bonds in a ceramic are stubborn, covalent, ionic, directional. You cannot trick them into flowing. You can only wait for atoms to diffuse, and diffusion is exponential in temperature. Double the rate and you climb 300 Kelvin. So you climb. That has been the deal since the 1890s. Heat. Wait. Open the furnace. Hope the part survived. It has been the deal for a very long time. Until a graduate student at Boulder pushed a button he should not have pushed. And the deal broke. The University of Colorado at Boulder, the engineering complex on the east side of campus. Rishi Raj's group had spent years on a quiet, technical question: how electric fields affect defects in ceramics. Field-assisted sintering, a niche corner of a niche field. In late 2009, a visiting student named Marco Cologna arrived from Italy. He worked alongside a postdoc, Boriana Rashkova. The project was routine. Run a small voltage across a zirconia disk inside a furnace. Watch what happens to the densification rate. Yttria-stabilized zirconia, 3% yttria, the standard ionic conductor. A disc roughly 3 millimeters thick, platinum electrodes top and bottom, sitting in a tube furnace. Hold the furnace at 850 Celsius, way too cold to sinter zirconia conventionally. At that temperature, in a normal experiment, nothing happens for hours. They had been varying the voltage in small steps, looking for incremental effects. On this particular run, they pushed the voltage higher than usual. And the current did something it had never done before. It spiked. Not by 20%, by orders of magnitude. The supply nearly tripped. Inside the furnace, the disk lit up, orange, white, visibly shrinking. 5 seconds later, the trace plateaued, the glow steadied. When they pulled the sample out, it was fully dense, 99% mirror gray. At 850 degrees, in under 5 seconds. They wrote it up, November 2010, Journal of the American Ceramic Society. 3 authors, Kolonia, Rashkova, Raj, a 4-page paper. By their own estimate, you would need to run a conventional furnace at 1900 degrees to match it. 1900, which is to say, impossible. For about a year, the result was greeted with polite silence. It is the standard reaction in material science when somebody publishes something that should not work. Other labs assumed the temperature was wrong, the geometry was wrong, the zirconia was contaminated. Then groups at Trento, at Oxford, at NIMS Japan tried to reproduce it. Vincenzo Sclavo and Mattia Biezuz at Trento got it on the first try. Richard Todd's group at Oxford got it within months. Hidehiro Yoshida at NIMS reproduced it on a different oxide entirely. The result was real. The field went in a single year from skeptical to crowded. By 2014, the Kolonia paper had hundreds of citations. By 2019, over 1,000. It is, on most counting methods, the most cited ceramic processing paper of its decade. Imagine a snowball rolling downhill through dry powder snow. The bigger it gets, the more snow it picks up, and the more snow it picks up, the bigger it gets. Now imagine the ceramic is the hill and the snow. Apply electricity. You start the snowball. There are 5 steps to the loop, simple individually, not simple together. You apply a voltage, a small current flows, Ohm's law. That current deposits heat, P equals I squared R, Joule heating. The heat raises the temperature of the sample. So far, nothing unusual. And now, step 5, the trick. The conductivity of a ceramic depends on temperature, strongly, exponentially. This is the Arrhenius law. Sigma of T equals A times e to the minus E over RGT. E is the activation energy. Rg is the gas constant. T is temperature in Kelvin. For a ceramic, conductivity climbs by an order of magnitude for every couple hundred degrees. Hotter ceramics conduct better, a lot better. Which closes the loop. More heat, higher conductivity, more current for the same voltage. More heat. The snowball is rolling. This is the gate. Any ceramic with a steeply rising Arrhenius curve is a flash candidate. Anything with a flat curve, pure alumina, most insulators, is not. Hold that thought, we will come back to it. Now the energy bookkeeping, the full heat equation. On the left, heat stored as the sample warms, density times specific heat times the time derivative. In the middle, heat flowing out by conduction, the Laplacian term. On the right, heat coming in, the Joule source, sigma times the gradient of phi squared. That last term is where electricity becomes heat. And because sigma depends on T, the source grows where the sample is already hot. Ian Hewitt, Andrew Lacey, and Richard Todd noticed something. If you average this equation over the sample, you get something much simpler. d theta dt equals f of theta minus g of theta. Heating in, cooling out. One variable, one time. Theta is scaled temperature. F rises exponentially because sigma does. G is the cooling, roughly linear. Plot F and G together, theta on the horizontal, rates on the vertical. For low voltage, F is small. It crosses G at a low temperature. The sample heats up a little, settles, sits there. Turn the voltage up, F gets steeper. The crossing moves higher, still stable. Turn it up more, the curves get closer, they almost touch. And then they kiss. Tangentially. One single point of contact. That is the flash threshold. Push a hair higher and the curves separate. F is everywhere above G. No more crossing, no more steady state. d theta dt stays positive. The temperature does not stop. In the simplest limit, drop cooling entirely. The math says theta equals minus log of 1 minus lambda T. Lambda packs voltage, conductivity, and geometry into one number. Plot it. The temperature rises slowly, then faster. At time t equals 1 over lambda, the log diverges. The temperature goes to infinity in finite time. Mathematicians call it blow-up. In practice, the sample does not explode. Two things stop it. Radiation grows as t to the fourth and eventually catches up. And, much more importantly, the operator caps the current. Every lab supply has two modes. Voltage control holds V constant. Current control holds I constant. When the current spike hits a preset ceiling, a few amps per square centimeter, the supply flips. Runaway becomes equilibrium. The temperature settles around 2000 Kelvin. The current sits at its cap. The voltage relaxes. And in those few seconds at 2000 Kelvin, the sample sinters. This is the trick. Flash sintering is a controlled bomb. You start a runaway. You catch it at the peak. You use the energy of the peak to do the work. And the line between settling and runaway is one inequality. Lambda greater than 2 over E times beta plus delta squared alpha. Lambda is heating. Beta and delta squared alpha are the cooling coefficients. Heating must exceed cooling by a factor of 2 over E, about 74%. That is the flash criterion, the entire phenomenon in 7 symbols. Hewitt, Lacey, and Todd derived this in 2015, 5 years after Cologne's experiment. It does not explain why flash sintering works. It explains when. But not everyone agrees that this is the whole story. There are, broadly, two camps. On one side, Richard Todd at Oxford, Yanhao Dong and Ai Wei Chen at Pennsylvania, and the Hewitt model itself. Their position is simple. It is just Joule heating, full stop. Todd's 2015 paper, co-authored with Zapata Solvas, Bonilla, and Wilshaw, fits the F versus G model to experimental current voltage traces. The fits are good. The model predicts the onset voltage to within a few volts. The sample, on this view, simply gets very hot very fast. The high temperature does the sintering, nothing exotic required. Dong and Chen, working independently, derive a similar onset criterion that fits across more than a dozen materials. They argue that if you account properly for the local temperature inside the sample, not the furnace set point, the densification rates are exactly what you would predict from textbook diffusion. There is no mystery. There is a thermometer error. On the other side, Rishi Raj himself, working with Hasan Naik, Sklavo, and others. Raj's argument starts with measurements, not theory. He points out that if you estimate the temperature from the black body glow of the sample, and you compare it to the densification rate, the diffusion you would need at that temperature is not enough. You would need to be hotter than the sample physically can be. Something else is moving atoms. His proposal: Frenkel pair avalanches, pairs of vacancies and interstitials created in cascades mediated by the electric field. Atoms hopping not because they are hot, but because the field has filled the lattice with defects to hop into. It is a different physics, electrochemical, not purely thermal. The Joule-only side responds. The black body temperatures are themselves wrong. The sample's emissivity is poorly characterized. The core is much hotter than the surface. Yanhao Dong's later modeling work suggests local hotspots at grain contacts, tiny regions running hundreds of degrees above the Bock. In a hotspot, normal diffusion is plenty, no new physics needed. Todd and his group point to in situ pyrometry that, when done carefully, gives core temperatures consistent with the diffusion rates observed. The hotspot picture is, by some measures, winning the publication race. The Raj side responds in kind. Hasan Naik and Marco Cologna have shown evidence of localized reduction at the cathode, chemistry that Joule heating alone cannot do. Samples flash-sintered in argon look different from samples flash-sintered in air. The microstructure carries fingerprints of an electrochemical event. Pure thermal models, the Raj camp argues, cannot reproduce those differences. Some flash-sintered samples come out black instead of gray. Color change without composition change. That is not a temperature effect. Mattia Biezu's and Vincenzo Sglavo's 2019 review canvasses both sides and lands carefully on "we still do not know." There are good experiments on both sides. There are strong personalities on both sides. And 15 years after Cologna's discovery, there is no consensus. The Joule camp says, measure the temperature properly and the mystery dissolves. The defect camp says, the temperature cannot be the whole story. Both are doing real science. Neither has been able to deliver the killing measurement. Back to the gate, Arrhenius. Every ceramic has a fuse temperature written into its conductivity curve. Some are short fuses, some are long, some have no fuse at all. Yttria-stabilized zirconia, the original, steep Arrhenius curve, flashes around 850 Celsius. Titania, titanium dioxide, flashes near 700, beautifully. Strontium titanate, 650. Zinc oxide, flashes near 600. Keria, around 500. And then there is manganese cobalt oxide, MnCO2O4, a spinel that flashes at 325 Celsius. 325, a hot oven. Pure alumina, on the other hand, refuses. Flat Arrhenius curve, no runaway, no flash. You can push it to 1200 Celsius and 1200 volts and watch nothing happen. Tungsten carbide, silicon carbide, most pure oxides outside the conducting families. They all refuse. The pattern is simple. If your conductivity versus temperature curve is steep, you can flash. If it is flat, you cannot. Salvatore Grasso at Queen Mary in London has spent a decade cataloguing these curves and predicting which oxides will flash next. Unless you cheat. There is a sister technique, older than flash sintering by decades, spark plasma sintering. Developed in Japan in the 1960s, refined by Hidehiro Yoshida at NIMS, and pioneered in the West by Eugene Olewski at San Diego State. Olewski and Charles Manier showed in 2017 that if you press the powder hard in a graphite die and pulse the current, you can get even alumina to flash. Flash SPS. The gate gets walked through. And the gate is wider than oxides. In 2022, a group at São Carlos, Brazil, pulled a glass into a glass ceramic in seconds. João V. Campos and Ana C. M. Rodrigues at the Federal University of São Carlos. And Isabella Lavagnini, co-author on both papers, the through line between USP's Pirassununga campus and CERTEV at São Carlos. Working with Isabella Lavagnini at USP and the CERTEV Center, the Center for Research, Technology, and Education of Vitreous Materials. Their material was LAGP, a lithium aluminum germanium phosphate, a Nazicon glass ceramic, a solid-state lithium-ion conductor. Conventionally, you crystallize this glass by holding it at 620 degrees Celsius for 12 hours. Campos and Rodrigues did it in seconds, at 500 Celsius, with 1 voltage pulse. Same gate. The glass has free lithium ions. Its conductivity climbs with temperature exponentially. Arrhenius opens the door. They named the technique Flash Sinter Crystallization, FSC, the first time anyone had crystallized a glass through the flash event itself. Now, the practical question. Why does any of this matter outside the lab? Conventional sintering, one of the most energy-intensive steps in the entire ceramics industry. Estimates vary, but a full afternoon of tunnel kiln operation can draw the daily electricity of a small town. Flash sintering, done well, can cut that energy by 90% or more. Hours become seconds. Acres of furnace become a benchtop rig. That changes what is buildable. Solid oxide fuel cells need dense, thin electrolytes, a few microns of zirconia. Conventional sintering coarsens the grain and ruins the film. Flash sintering, in seconds, can densify it without coarsening. Next-generation battery cathodes need dense lithium-ion conductors. Same story. And on the electrolyte side, the LAGP that Campos and Rodrigues flashed in 2022 is a candidate solid electrolyte for all solid-state lithium batteries. Their flash-crystallized samples hit room temperature ionic conductivity of 2.26 times 10 to the minus 4 Siemens per centimeter. Higher than the same composition prepared by 12 hours in a conventional furnace. Faster manufacturing, better material. 3D printed ceramic parts come out of the printer fragile and porous. Putting them through a conventional kiln warps them. Flash sintering, done in place on a printing bed, done before the geometry has time to deform, is being actively explored. And then, dental crowns. In 2024, the São Carlos group came back with a second paper. Campos, Lavagnini, Rodrigues, joined this time by Edgar Zanotto, the world's leading glass ceramic scientist. Their target, lithium disilicate, the glass ceramic at the heart of Ivoclar's Emax CAD, the standard material for permanent dental crowns. Conventional crystallization, hours at 620, then 30 minutes at 830. Their version, Power Ramp Flash Crystallization, does it in seconds, at 360 Celsius furnace temperature. Below the glass transition, below the temperature where atoms are supposed to move. Vickers hardness, 6.8 gigapascals. Fracture toughness, 1.5 mppa root meter. Indistinguishable from the conventional product. The dental prosthesis market in 2024 is worth $7.55 billion a year. A faster way to crystallize a crown is not a small thing. Companies like Lucidian in the UK have built pilot lines. NIMS in Japan runs an industrial-scale demonstrator. There are patents, there are spin-outs, there is, slowly, a commercial story. It is not yet at the scale of conventional sintering. The challenges are real. Non-uniform heating, electrode contamination, scaling beyond small disks. But it is one of those rare lab curiosities that, if it scales, changes the energy footprint of an entire industrial process. From a graduate student's accidental experiment to a candidate for industrial decarbonization in 15 years. Not bad for a 5-second result. Marco Cologna is now at the European Commission's Joint Research Center in Karlsruhe. Rashkova is at Montano Universität Leoben. Raj is still at Boulder, still publishing on Flash. The 2010 paper has been cited over 1,500 times. One last piece of math, the closing argument. The Flash criterion, written back in lab variables. This is the inequality the engineer actually uses. On the left, the heating term. The material's Arrhenius constant, the activation energy, and, the part you control, the voltage per length squared. Times an exponential factor that depends on furnace temperature. On the right, the cooling, convection, radiation through the surface, geometry. Heating must exceed cooling. That is the whole sentence. Plot it as a regime diagram. Furnace temperature on the horizontal, voltage per length on the vertical. Above the curve, the flash region. Heat in beats heat out. Runaway. Below the curve, stable, dull, hours of furnace time territory. Drop in Cologna's 2010 data point. Zirconia, 850 Celsius, the voltage they used. It sits exactly on the boundary. Drop in the rest of the literature. Todd's titania, Sclavo's Caria, Yoshida's zinc oxide. They sit on the boundary too. The theory and the experiments agree. If anyone ever measures the true core temperature of a flashing sample in real time, the mechanism debate ends. Until then, the equation is what we have. It is enough to design experiments. It is not enough to explain them.